So thank you very much, Arindam, for those nice lectures. Now let us welcome Partha Paul to continue the lectures on celestial holography.
So, am I audible, right? Okay, so after this nice lecture by Arindam, I hope at least like you think that there could be a holographic correspondence between the quantum gravity in 4-dimensional asymptotically flat space-time and some 2D quantum field theory which lives on the celestial sphere. So, so here actually, okay, so the goal of my lectures will be like to study this 2D quantum field theory as much as we can. But before that actually, so I'll go through some very basic stuff about the quantum field theory. So this may be trivial to most of you, but I will go through them anyway because this is the main ingredient. This will be the main ingredient for the later part of my talk. So this is something called the classification. So this is something called the classification of one particle states under the Poincare group, which is the ISO3 inhomogeneous Lorentz group. Why these one particle states are important? Because the main object of interest in quantum field theory is the scattering amplitude, and that scattering amplitude is defined using this one particle state. So for example, an endpoint amplitude AN, so that is defined as out as in. For this 0 subscript here, it means that this in state, it is basically the eigenstate of the free Hamiltonian H0, and this in state, this is written as the product of the one particle states. Something like this. So these are basically called the one particle states. So P1 is the momentum of the particle, and okay, we will see. I mean, like, what does this mean? So now, as we know that the Poincare symmetry, it has total 10 generators. So the 4 momentum generators, which are basically responsible for the 4 translations. There are the boost generator. So I runs from 1 to 3. So these are basically the boost generator, and there are then these 3 rotation generators. It is antisymmetric in IJ. Okay, so you also know that the symmetry transformation in QAP, it is represented by some unitary operator. Okay, so for example, the translation, this Lorentz transformation is identity, and suppose the translation is by some 4 vector A, so that is represented by minus I A mu B mu. And since the translation operators commute with themselves, so usually what we do is that in QFT we usually choose the eigenstate of this momentum operator. So I just write them as some p comma sigma. This p is basically the momentum of the okay. So throughout all my lectures, I will only be talking about the massless particles. So this is the momentum of the massless particle, that is the null momentum, and sigma is some other level apart from this momentum. Okay. So this translation operator, for example, it acts on this p sigma is something like this, just a phase factor. Okay. So now suppose we want to study the Lorentz transformation properties of these one particle states. This theory actually, this is the theory of massless particles. It could be like spin 1, spin 2, anything. Okay. This sigma level here. Okay, scalar also could be there. Yeah. Right now what I am discussing, I mean, okay, so I mean like massless scalar could be there. I mean right now I am just talking about some free theory. I am just trying to classify the one particle states, right?
Yeah, but I'm just saying like the things you're talking about is just some free case theory, some just standalone case theory of gravity or something like that.
Yes, just massless particles theory. Yes.
What does lambda equal to 1 mean?
Meaning there is no Lorentz transformation, only translation.
Lambda matrix is identical.
Yes. Yeah. So to study the Lorentz transformation property of this one particle state, so what we do is, okay, so basically what we want to calculate is lambda and a equals 0 because there is no translation. I am now actually just want to study the Lorentz transformation property. So I want to study this thing, u lambda. What is u lambda acting on p sigma? So to do that, suppose you apply this 4 momentum operator p mu, then you can insert an identity operator which is basically nothing but u lambda inverse p mu. Now we know what is the Lorentz transformation of this 4 momentum operator. It is something like u lambda some lambda mu p sigma. Okay. So then this 4 momentum operator acting on this thing, it will give you some lambda mu small p nu. Okay. Then you can take this to the left hand side. So this is something like lambda p mu. So then what is this 4 momentum operator doing on this state? It is basically so this state is basically kind of an eigenstate of this not kind of an, this is an eigenstate of this p mu operator. So what we can do then we can write this state something like this, right? So only sigma can change and p will be changed by this lambda p. So this can be written by some sigma prime sigma. It can depend on lambda and p, and then p will change to lambda p sigma prime. So you understand this, right? I mean this state, it is an eigenstate of this 4 momentum operator p mu. Okay, but with the eigenvalue like lambda p, and this index sigma, it can change. Okay. So actually now we want to find the matrix, these matrix elements C sigma prime sigma. Okay. So to do that, actually what I will do now is to introduce some notion called the little group. Okay. Okay, so suppose you take a null momentum k mu, okay, and then you make some Lorentz transformation. So this is some reference null momentum. Suppose you start with some k mu equals to say some 1 0 0 1. and you make some Lorentz transformation to get the most general null momentum p mu. Okay. Now the one particle state, so p comma sigma, it is defined as some normalization factor u of lambda p acting on this k sigma. This is how I am defining my one particle state. Okay. So you just take this state k comma sigma where k is given by that. Then you make this particular Lorentz transformation, you get the one particles, and this NP is some normalization factor which I will fix later. So now suppose, okay, so our A wants to study the Lorentz transformation property of this one particle state. So this will be something given by like this. L depends on the choice of k. Yes, I mean, like, yeah, of course.
So like L is a function of both P and K. So
yeah, but since k is like I have chosen, so that's why I have not written k. But yeah, it will depend. Yeah. So I mean, it is the particular Lorentz transformation which will take you from k mu to the. So of course, I mean, like, it will be different for different A. So this will be something like n of p u of lambda u of L of p. So the matrix multiplication rule that will tell you this will be something like u of lambda LP. Now what you can do, you can insert an identity operator which is something like u of L lambda p u of L. This is the definition. This is right. This is what you are asking, right? So this is the definition of my one particle state. So this is a particular Lorentz transformation which is not changing my sigma level. It is only changing the form momentum.
how do I know that such a transformation exists? Because previously you showed that the Lorentz transformations generically change sigma levels as well, right?
Yes. But okay, so that was okay. So I mean,
This is definition for P sigma.
I mean, so I think you can always find such a Lorentz transformation. I mean, like,
A spin object will certainly transform, right? It will mix under the.
no, I mean, like, okay, so of course, I mean, like, here I am choosing a particular k mu, and this is how I am defining my sigma level. This is like the definition of the sigma level, how I am like defining it.
Yeah, but whatever object you have, it will have some momentum with the reference momentum that you are saying. But then that, let's say that particle will have some spin level also, right? So when you do any transformation, in fact, we have not even assumed what the transformation is like. Generically, they will mix.
No, I don't think so. I mean, then actually, okay, so I have not told you like what is the definition of my one particle state, right? Now I am telling you this is the definition of my one particle state. We start with some state, and you make this particular Lorentz transformation, you get this. So under this transformation, my sigma level does not change. That is what I am just saying.
This is like choosing a particular C sigma prime sigma. It's like, are you saying that C sigma prime sigma is delta sigma prime sigma?
That is what actually it will come out. That is what it will come out at the end.
Exactly. So might as well you can assume that it is mixing and then even.
Well, this is how actually I think it is done to find the representation of this group actually. This is something called induced representation, but okay.
But you eventually want to get to the fact that C sigma prime sigma.
Eventually it will lead to that fact. Yeah. So, yeah. Yeah, so, okay.
What is the thing that you've written in that middle?
It is like u of L lambda p and u L lambda p inverse. Okay, this is some identity operator I have written in this way. So, this is something like u of,
It won't be clear for the
this middle part.
Can you erase and write?
So this is again the matrix multiplication rule, P inverse lambda L of P. Now see what is this Lorentz transformation doing. So first this Lorentz transformation, it is taking your k vector to p vector, and then this lambda, okay, it is just any arbitrary Lorentz transformation, and then this particular Lorentz transformation, it is again, okay. So first, so let me write it again. So first your k mu, it is going to p mu for this particular Lorentz transformation. Then this lambda is taking you to lambda p mu, and then again this inverse Lorentz transformation, it is again takes this back to the k mu. Okay. So this is a particular Lorentz transformation under which k does not change. Okay. This is so this is a subgroup of the full Lorentz group, and this group is called the little group. Okay. So let me write this W lambda comma p is okay. Sigma can change. Yes, sigma can change. Okay. So then, so what it is doing then? Let me, so then W mu nu k nu is equals to k mu. Okay. So the k mu does not change. So now what I want to do is that I want to find this particular Lorentz transformation. Okay. So to do that, actually, okay, I won't go through that, but I mean, like, what I can tell you is that, so I mean, like, if you work out the details, so then this W mu nu, let me write it as some W. So W of lambda p, it will be given by these two particular Lorentz transformation, S of alpha comma beta, and then R of theta. Where this R of theta, actually it should be clear from this 4 vector itself. If you see, if you make a rotation in the 1-2 plane, then this vector does not change, which is basically the R of theta. And this S of alpha beta, it has this particular form. One plus zeta alpha beta minus zeta alpha 1 0. So I am using this signature, okay, minus plus plus plus. And this zeta, so this zeta is alpha square plus beta square by 2. So under this particular Lorentz transformation, we see that this k mu does not change, and one can check that these two in fact these two elements S and R, they among themselves they actually form two different abelian group. That means
Dependent on the choice of k.
oh no okay, so no, that is not. I mean, like, of course you can make some other k and you will end up getting the same group. This group has a name. No, k is time, like, then the group is different actually. Yeah, so as I was saying, so they form two different subgroups. So for example, S alpha beta. So S alpha bar, beta bar, S alpha beta. This is S of alpha bar plus alpha, beta bar plus beta. That you can check from the matrix multiplication rule. And this R of theta bar. So both the things S and R, they form two different subgroups. Okay, and this particular group, this W, it is called the ISO2. Huh?
Linear is level relation or like this thing is beta alpha beta is influence for alpha beta is.
Yes, that's what I am doing. This matrix that I have written. Yes.
So I'm getting confused. This seems like the alpha and betas are factorized or something, right?
Oh, okay, sorry. No, it's clear right now.
I'm just saying like this seems like alpha translates on its own, beta translates on its own. Like I'm seeing
Huh.
like a factorized thingy, but it's not a factorized thingy. Alpha and betas will mix, right? Oh yeah.
Okay, actually I don't understand, but let me write this thing in terms of the operator and all these things, then actually I'll get back to you.
What I was asking is that in that first line that you wrote down, the product of two S's, is there any, like, are you assuming this is true till all orders, like for any value of alpha and beta is this relation true? Like for alpha
Okay, that I think also should be true. Yeah.
But then it seems like alpha and beta like two factored parts of the group.
Then it looks like alpha and beta should be two different things. Yes, I think so, because yes, I think so. Yes.
Some rotation they will mix.
Yes. Yeah, I mean, like for example, if you compute the generators for them, so they actually commute. I mean, like if you call the A and B, they commute also among themselves. Yeah.
No boost and no rotation will become there, right?
This is the combination of boost and rotation. Let me write out the generators, then actually, okay.
One question. So you're saying for any null KMU, this group shouldn't.
This group should be true. This group is called the ISO2 actually. Yeah.
So then if you rotate KMU with the 3 rotation, then their W mu nu on that also should be the same, is it?
Well, no, actually W mu nu will change, right? If your K changes, then you will have a different set of Lorentz transformations, right? I am just telling you that you just choose a K mu and you are trying to find a Lorentz transformation which does not change that K mu, and that group will be like the ISO2, no matter what K mu you choose. I have chosen this K mu for like the simplification.
W mu nu is a generic element of that.
Yes.
So it should act on any KMU you choose.
Yes.
And if the KMU happens to be Maxwell,
So from this, can you show that from this W mu KMU equal to KMU?
I mean, so you are saying that okay, so from this S into R theta, so starting from this matrix, if I multiply it with on KMU, then actually it will give me the KMU. That actually it will happen, that is for sure.
Not that. There is that relation W mu nu acting on K nu, being KMU. If I use this, can I derive that W mu nu acting on rotation of K should give me rotation of K?
That should happen actually. I mean, like you are saying something like this most probably, if I understand it. So W mu nu, some R K mu, that should be something like R K mu, right? That should happen actually, yeah. But you have to like check it, yeah. I mean, group is same. I mean, like, okay, this same W mu nu may not work. The group is same. ISO2 is same. Yeah, group. I think now you can actually do it for infinitesimal transformation, infinitesimal alpha beta. So then actually you have to write this W mu nu as. That's what I am going to write. So W mu nu is like delta mu nu plus some say omega mu nu. Okay, and this omega mu nu, it will have this form. So 0 minus alpha minus beta 0, alpha 0 theta minus alpha, beta minus theta. Okay, and now you know any unitary operator. If you make the transformation like infinitesimal, so u of 1 plus omega, it is given by something 1 over I by 2 omega mu nu j mu nu, and then from there actually from this omega mu nu, if you put it here, so you can then actually write this as some I identity plus I alpha a plus some I beta b plus I theta j3 plus the higher order terms. But this a, it is like given by j of 1 0, which is the boost in the first direction, minus j of 1 3, which is the rotation in 1 3 plane, and this b is given by j 2 0 minus j 2 3, and this j3 is the j12 basically, I mean the rotation around the third axis. Okay. B A, yes, j10 minus j13, yes, and now you can actually calculate the commutator a comma b, that will give you 0. You can also calculate what is j3 comma a, that will give you plus ib, then j3 comma b. So this is the group structure of iso R2. So now what you were saying, actually this A and B actually commutes among themselves. Yeah, and so that since A and B commute among themselves, so what we can do is that we can choose the eigenstates of these two operators simultaneously, right? We can diagonalize them. Them simultaneously. So what we can do is that we can choose an eigenstate. See, we are actually okay. So we were actually working on this particular Lorentz transformation. We wanted to see actually how this particular Lorentz transformation acts on this state. So if I call this as some u of w, say, which is nothing but u of L inverse lambda p, lambda L of p acting on k sigma. So under this transformation actually k does not change, only sigma change. So this will be something like sigma prime d of say sigma prime sigma, and it will depend on this lambda comma p k of sigma prime. So we are trying to find this matrix representation, this matrix elements. Okay. Where only sigma is changing. So and this is basically this is the group which I am now talking about, this iso 1,2. So if you now want to actually so if you want to find a representation, then what you will do? So you saw that actually this AB commutes, so you can diagonalize them simultaneously. So what I'll choose an eigenstate of these two operators. Okay, so that I will write something like a comma b, where a is the eigenvector, and like a is for a and small b is for capital B. Okay, so when this operator a will act on this, it will give something like a b, and this b operator acting on this, it will give small b. Okay, so now I don't need to actually, I have just told that I can, right? Because they be commits with themselves. Now I'll show that you cannot actually, because there will be a problem. Okay. So okay, so here I have chosen eigenstate which simultaneously diagonalizes this A and B. But now I will tell you there will be a problem if you do this kind of things. So for that actually you can check that this particular A is alpha beta. So under rotation it changes like this. R of theta bar, sorry, R theta inverse. This that you will see, yeah, that you will see. Yeah, exactly. This rotation around in the 1-2 plane. So this will be something like a case of alpha cos theta plus beta sin theta. So minus alpha sin theta plus beta cos theta. So what does it tell you? That if you actually choose such a state, okay, and then if you can actually then make a rotation, right, by this r of theta, that I am calling some state like I mean this will become something like a cos theta plus b sin theta minus a sin theta plus b cos theta. And then if you act on this state by the operator A, let me call this state as A B B theta. So this will give you some A cos theta plus B sin theta A B theta. So what we are seeing is that, so actually if we choose this eigenstate for a particular A and B, then there can be actually infinite number of such actually if I choose this eigenstate KB, then the eigenvalues of A and B is basically given by small a and small b. But actually if I find one of them, then I can find actually infinitely many of them, a continuum of them. But we know that massless particles don't have such degrees of freedom. So that's why what we will do is that we will set A equals to B equals to 0. Okay. So then what we are left with is basically this generator J3, right? This generator J3. Okay. They don't no, because this A has this J10 boost, right? Yeah. So what I am saying is that, so suppose you start with this eigenstate A comma B. So it has the eigenvalues for these two operators A and B given by small a and small b. Now suppose you find one such thing, then actually what you can, so if you have found one such thing, then you can find a continuum of them, right? Just by making the rotation. So there are like continuum of eigenstates of these two operators A and B with this continuum of eigenvalues, which is not true because massless particle doesn't have continuous degrees of freedom. So then we are left with only R of 3 and acting on K sigma. Okay, so U of W I can write it as U of S alpha beta u of r theta acting on. Yes, that's why I am setting a equals to b equals b. Then the problem is solved, right? Because like this will be 0 simply. Sorry. A and B annihilates the state.
So how do you get the two states? Like there is no continuum, but like initiate the two states.
That's what I will get from this r of theta. So u of s alpha beta, you can write it as e to the I alpha a plus I alpha b, and u r theta, you can write it as I theta j3 acting on this k sigma. Okay. So as I have chosen that these are the eigenstate of a and b with 0 eigenvalues, so these won't do anything. So e to the I theta j3, it will give you e to the I theta, and this sigma you can choose this is an eigenstate of j3, so this will be just the eigenvalue of j3, that is the sigma. So e to the I theta sigma k comma sigma. Okay. Now you see this j3, it was the third component of the angular momentum, right? And this sigma, it is basically giving you the value of the angular momentum in that direction, that is the third direction. And our massless particle, if you remember, the k mu that I have chosen, it was actually in this form 1, 0, 1. That is, it was pointing in the third direction. So that means this sigma is giving the value of the angular momentum along the direction of motion. This is which is we call the helicity of the particle. Okay. So basically then from here? No, I have chosen that this is the eigenstate of J3 and this sigma is the eigenvalue of J3. Because anyway this is just annihilating the state. So thus but if you see, I have written this U of W acting on K sigma as some matrix representation D sigma sigma prime, and this D sigma prime sigma I have found like this e to the I theta sigma delta of this theta can actually depend on lambda p sigma delta sigma prime sigma. I think this is what Chandramouli was talking about. So this is d sigma sigma, this sigma prime sigma is basically nothing but the delta sigma prime sigma. Hence, I'll now finally write what is the Lorentz transformation of the one particle state. So u of lambda acting on p comma sigma. So this was something I'd written in some somewhere. So this will be something like some normalization factor, and there was this u of L lambda p, then there was this u of W acting on this k comma sigma. This was the thing, right? Yeah. Then this normalization factor, then u of A lambda p. This u of W acting on this k sigma, it is giving me e to the I sigma theta lambda comma p delta sigma prime sigma, but that will just give me again k sigma. Okay. Then you can write this as e to the I sigma, and then u of L lambda p acting on this, and under this Lorentz transformation, as I have told, only k changes, sigma does not change. So that will give you lambda p comma sigma. And this normalization factor I am writing. This is normalization factor. Usually people choose when they do this inner product kind of thing. So this normalization factor will be something like lambda of P0 by P0.
However, you see sigma prime sigma related to d sigma prime sigma.
This is from here actually. So I was just trying to find a representation of the little group, and that I have written in terms of this matrix representation d sigma prime sigma. Okay, and I have just written this u of w like this way. That is given by nothing but this e to the I theta sigma, right? Sorry, this e to the I theta sigma k sigma. Okay, so now you can compare what would be the d sigma prime sigma. It should be like e to the I theta sigma delta sigma.
You're also referring to c sigma prime sigma.
That was like when I was just trying to find the representation of this u lambda acting on this p sigma, right?
So
Now I have just, okay, I have trans.
no, I'm just asking, like, where did that enter this calculation? Like,
So okay, so initially, so let me just then recap what I have done. So this is the Lorentz transformation property of the one particle state. This is what you see, right? Now let me recap what I have done. Then I think the So I started with this u lambda p comma sigma. That can be written something like c sigma prime sigma. Something like this. Now we have to find this matrix elements c sigma prime sigma. Okay, but okay, so this should be sigma prime. Now I am telling that instead of trying to find these matrix elements, what I will do, I will take a different tool actually. I will go through via this little group element. So then actually I have transformed this whole problem into something like this. I will write this u lambda p comma sigma. This I will write like some normalization factor u of a lambda p, then u of w acting on this k sigma, and this u of w acting on this k sigma, it is giving me sigma prime, because this is the representation of the little group, so the matrix elements will be different. So this will give me this sigma prime sigma. It will depend p also, and that will be something like k comma sigma prime. So instead of finding these matrix element, I have found this d sigma prime sigma.
okay, but can you find c sigma prime sigma from this, or
No, I mean like see, I mean like, but I have found ultimately this, right? So from I have ultimately found this, right? Something like this. So this should be C sigma prime sigma, right?
this means that under Lorentz transformation the sigma doesn't change, but any kind of Lorentz transformation?
For the massless particles, yes, I mean like this is the Lorentz transformation for the massless particles, right?
Helicity should not change.
Oh, I mean like, is there any question? So these all things actually reference for this is the chapter 2 of Weinberg volume 1. So this is how actually he found the Lorentz transformation properties of the one particle states. Actually now okay, so now actually I'll This is clear to all of you, right? So now actually, okay, so Arindam has said that actually we are looking for a 4D 2D kind of holography. So so the central importance for this kind of 4D 2D holography is the isomorphism between these two groups. SO1, 3 is isomorphic to SA2, C by Z2. I'll explain what is Z2. So SO1, 3 is the group of Lorentz transformation in 4-dimensional Minkowski space-time, and this SL2, C, it is the group of global conformal transformation on the Riemann sphere. Okay. So just to easily see why.
This group, little group, is something which leaves one particle massless state invariant. That's all it is, right?
Which leaves the momentum of the one massless particle invariant. Under little group, sigma can change, not the k. Okay. Ultimately did not change, but I mean, like, we allowed initially that it can change, right? Then we found that it became delta sigma prime sigma.
The fact is that you have a sigma which is some quantum number. We don't know what that quantum number is, and then we want to find in general if you have a momentum that does not that is, I mean, so you take this reference k and then you do some specific Lorentz transformation and you get some arbitrary momentum. You want to find those transformations on the states where the sigma quantum number is not changing. And when you try to do this argument, you see that it does indeed not change, but there is an overall scaling that happens.
No, I think it is basically telling you that under Lorentz transformation sigma does not change, but if you do it for the massive particle, then you will see that this particular quantum number will change. Then actually you will find that little group will be like, okay, so for the massive particle, I have not done it, so the momentum that we choose is the 1, 0, 0, and from here actually you can guess the little group will be like the rotation, the rotation, right? I mean, so then actually you will see that under that little group the quantum number which is like the J3, I mean this, for the massive particle it is not helicity, right? Massless it is helicity.
Helicity is a good quantum number.
Yes.
It does not change under any Lorentz transformation.
Yeah.
Massless, for massless particles.
For massive particle it will be spin, so that will change actually, right? So yeah, so that this is what actually this thing is telling you.
Yeah, no, my confusion was that there was this equation where you wrote down. I think the first time when you introduced the little group transformation equation.
Yes.
I think W acting on k comma sigma gives you k comma sigma.
W acting on k comma sigma is giving you k comma sigma prime, and there was this d sigma prime sigma. So we are allowed to change the sigma prime, but what will I mean, like at the end, what we saw is that it does not change.
Okay, fine.
Yeah. But for the massive particle, you will see that the spin will change. Okay. So okay. So just to easily see why this isomorphism works, so what we'll do is that you just start with some 4 vectors, say x mu. Okay. Okay, so by the way, this SO1, 3, this Lorentz transformation, this is the 4x4 matrices, right? Whereas these SL2, see, these are like some 2x2 matrices. Yeah. So just to easily see why this isomorphism works, so first we'll start we'll start with the 4 vectors, say x mu, and then we'll write this 4 vector as some 2x2 matrix using this thing. So x equals to x mu sigma mu. Okay. What is this sigma mu? The 0th component of sigma mu is the identity operator, and the other 3 are the Pauli matrices. Okay. Then using this, you can write this capital X as x0 minus x3, x1 plus minus x0 plus x3, x1 minus ix2, then x1 plus ix2, then minus x0. Okay. Now you can calculate the determinant of this 2x2 matrix. It will give you minus the norm of actually it will give you the norm of this 4 vector minus x mu, x mu. If you calculate the determinant of this 2x2 matrix, So now suppose you make a SL2C transformation of these two matrix, okay, 2 by 2 matrix. So the SL2C transformation, suppose, okay, so the SL2C transformation are actually represented by these 2 by 2 matrices A, B, C, D, where the determinant of this matrix AD minus BC, that should be equal to 1. Okay. Now suppose you make some SL2C transformation of this 2 by 2 matrix X. So that will be something like M dagger X M, right? So let call that a transformed 2 by 2 matrix as X prime. Now if you calculate the determinant on both sides, then the determinant of M is 1. So what you will get is determinant of X equal to determinant of X prime, right? And you know that determinant of X, this is nothing but the norm of this 4 vector. And this determinant of X prime is nothing but the norm of the transformed 4 vector, minus X prime mu, X prime mu. Okay. So what it is telling is that this under this SL2C transformation, the norm of the 4 vector that you started with, that does not change. And this is what basically the Lorentz transformation does. Okay. So that tells you that there is an isomorphism between these two groups. Okay. Now from here you can see that if you change AM by minus M. Huh?
It's just a subset.
No, actually you can actually, okay, I mean there is another, like you can just map the generators also. From there also you can get this isomorphism, but that is not I am going to do. So now actually from here you can see that for M goes to minus M, this thing still works. Okay. So actually then what you are seeing from here is that for each plus minus M, you will get only one Lorentz transformation. That means for 2 of the SL2C matrices, you are getting one Lorentz transformation. So you have to subtract half of them. That's why actually here this G2 means. That's what this G2 means. Okay, you have to just get rid of those half of the SL2C matrices. Okay. Okay, so now to make this isomorphism more precise, okay, so just now to make this isomorphism more precise, meaning that how given a SL2C matrix, say for example, you can actually write down all the elements of the Lorentz matrices, for example. What we will do is that suppose you take some 4 vector x nu, and then you make the Lorentz transformation. Okay, and then you take the 2 by 2, and then you construct the 2 by 2 matrices. Okay. So that should be equal with what is like, you first take the 4 vector x mu, then you make these 2 by 2 matrices, and then you make a SL2C transformation. Okay. So from this equation actually you can actually see like what is the lambda mu in terms of the ABCD. Okay. For example, okay, so I am not writing down the matrix. So for example, lambda 0 0, it will be given by like half of A bar plus BB bar plus CC bar plus DD bar. So one example is that suppose you, I am just giving one example. So for example, you consider the boost in the third direction. So that is given by, so this is the third direction. That is given by cos chi 0 0. This chi is the rapidity. Okay, and the corresponding SL2C matrix for this particular boost will be given by m equals to plus minus e to the chi by 2 0 0 e to the minus chi by 2. This is just an example. Okay. I just told you that, I mean, so I wanted to write down each of these Lorentz transformation matrices element in terms of the ABCD or these SL2C things, right? So I just told you that from this equation you can do that, okay? And here is just an example of how like the lambda 0 0 looks like. And this is an example. For example, the boost in the third direction in terms of the Lorentz matrices looks like this. Whereas in terms of the SL2C matrices, it looks like this. Now I will talk more about the SL2C transformation. But now actually from the momentum space, okay. Okay, so now I'll actually go to the momentum space, and suppose since I am dealing with the massless particles, so the momentum of a massless particle is basically a null momentum. And now suppose you introduce two complex variables z and z bar in this way. So z is p1 plus I p2 by p0 plus p3, and z bar is okay. Huh. I will just write it in. You can just erase the minus. Yeah. Okay. So now actually what you can do is that. So or rather actually it is in a different way of writing the null momentum that Orintham has written anyway. This is another way of writing this. So E1 comma this would be like z plus z bar by 1 plus z bar. And then 1 minus z bar by 1 plus z bar. So so the null momentum you can always parameterize in terms of this z bar and another, like this is an energy scale. Okay, and now from the Lorentz transformation properties of this P1, P2, P0, P3, you can check that. So I have given you how lambda looks like in terms of the ABCD. So you can check that Z goes to P0 plus mod P3. What? P3 will be plus minus anything, then actually it will change minus P3. Yeah. It is just P3.
Minus P3, but then P1 when P2 will be 0. I think you remember the case when P3 is minus P0, but I think then P1 and P2 would be 0, right? It's a massless
You mean the 1 0 0 1, but then P1 plus P2 is 0 even if P3 is plus P0.
No. I mean, like, I think you can do it for P0 minus P3 as well. There is no problem.
No, Akhil is asking what if P3 is minus P0?
Oh, you are saying that if P3 is minus P0, then what will happen?
More P3 or just P3? That's what I asked.
Acha, sorry. You are asking if P0 is minus P3, but in that case, yeah, exactly. I think in that case, P1, P2 will also be 0. See, ultimately you have to satisfy this relation, right? P square is equals to 0. Ultimately, you have to satisfy this relation. So, if P0 minus P0 square plus P3 square is 0, ultimately P1 square plus P2 square has to be 0. That means P1, P2 is also 0. Yeah, he's right. Yeah. But I am not talking about those special momentum things, right? Null momentum. There could be other values of P, right? Yeah. Yeah, exactly. Yeah. So this Z will get transformed to this Z prime. and this that will look like z prime is az plus b by cz plus d, and z bar prime will be a bar z bar plus b bar by c bar.
Say given as b to 0. Okay, so z and z bar are 0.
Yes.
The way you have written it, you seem to get only e times 1 0 0 bar. You don't seem to get 1 0 0 minus 1. It's suppose that the north and south pole will come and you have to go to a different coordinates to get the other pole. 1 0 0 minus 1. So
Right.
1 0 0 minus 1.
So okay.
Go to a different coordinates to get that.
No, actually.
Yeah, so you have to go to different coordinates. One base coordinate.
I think this is something like the stratigraphic projection. Like I mean, like either you are projecting it from the north pole or you are projecting from the south pole. Something like that actually. So okay, so what I am trying to say is that under the SL to C transformation, so this Z bar they are trying SL to C the Lorentz transformation, they are transforming in this way. Okay, where this determinant AD minus BC that is equals to 1. Okay, so now what I want to say is that this Z bar they are basically only tells you that I mean like how this null momentum is actually directed. That means that or I mean okay, so let me be more precise. How can that be happen? So suppose for example, if your null momentum is directed along the third direction only, okay, that means when P1 and P2 is 0, okay, or rather your P mu is something like this, E 0, 0, this E is greater than 0, that's what we were talking about. So then actually what you will see is that this Z and Z bar is equal to 0. Okay, so what is this telling us? Then do you need that board? So what is this telling you is that all the null momentum which are directed along the third axis, they are getting mapped to this point z equals to z bar equals to 0. Okay. Now what I am trying to say is that in fact actually this z bar, this coordinate z bar, it parameterizes the space of all possible null momentum direction. Okay. So just to see that, I mean just to see that, what you can do is that you can take this null momentum say e comma 0 0 and you make a rotation, okay, to get this most general null momentum say, which is given by e comma e sin theta cos phi then for this most general null momentum you can see that z is given by tan theta by 2 e to the I phi and z bar is so the z bar, it only depends on the angle, I mean like the direction of the null momentum, and so and this basically forms a two sphere. So that means that the space of all possible null momentum directions basically forms a two sphere, and z bar are the coordinates on that sphere. I mean, you can also like calculate, say for example, dp square, a line element on the null cone, and you can see that there will be something like 0d square plus some 4 by 1 plus z bar square dz bar, something like this. So this is again telling you that this z bar, they are basically the forming a two sphere. Okay. 0 is this is a degenerate metric actually. Huh? Yes. So that's why I'm saying this is only telling about the direction of the null momentum, not the magnitude of the null momentum. Only the direction is important. Yes, it's some kind of topological S2 maybe. What is it called? I mean, like it can be like any S2 actually on that. Yeah. Yeah. Is that time over or what? Okay, so I mean this is the, okay. So in momentum space, so for example, this is your P0. So this is the basically two sphere, and z bar are the coordinates on that two sphere, and this dp square meaning the massless particles, they always lie on this null line, right? So if you calculate the any line element on this null cone, that is what I am calling dp square. Okay. E square, no, E square won't come actually. You can calculate. So what is the take-away message from this actually just is that for any massless particle in four space-time dimension, you can always parameterize your massless momentum by this equation. And this z bar, it is basically parameterizes the space of all possible null momentum direction. I'm again emphasizing on the direction because that will be important when I talk about the conformal primary basis and this literary group concept. Okay. And this z bar under Lorentz or SL2C, we have seen that the Lorentz or SL2C, they are basically isomorphic to each other. So under Lorentz or SL2C, so this z and z bar, they actually transform in this way. Sorry, z bar plus d bar by c bar z bar plus d bar. These are the actually coordinates on the celestial sphere. Okay, there are two reasons for this. Since I am talking, okay, I am talking from the momentum space perspective, but
first, what is the equal?
Sorry. Or rather, let me call it in this way, lambda z actually. Lambda z means this thing, I mean the Lorentz transformation. Okay, so this is this z bar, they are basically the coordinates on the celestial sphere. There are two reasons for this. I'll stop after this explanation. So actually, first of all, the transformation property you can see. So the transformation property of this z bar is like the transformation property of the celestial coordinates z bar. Okay, and the second thing is that this z bar is only telling about the direction of the particle, and the direction of the particle is what actually basically gives you the celestial sphere, right? The all possible directions, right? That is what is basically essentially the celestial sphere. So yeah, so this is where I will stop, maybe, yeah, and then.